Today we're going to continue. We're going to talk about a new notion, really, really interesting notion, in my opinion, called probabilistically checkable proofs. I'll explain what it is. So we're going to define this notion, and we're going to construct it from the GKR protocol. So you'll kind of see not only the definition, but you'll be able, after this class, the hope is that you'll be able to construct a PCP. If you need to construct a probabilistically checkable proof, you'll be able to do that. So that's going to be the first part of today's lecture. And the second part of today's lecture is actually going to be the first time we actually use cryptography. So far, this class has not been at all about cryptography. Everything was information. It was actually complexity theory. But today is going to be the first time we're going to move into cryptography. And as we'll talk, we'll see that doing this information theoretic proofs where you say, okay, no prover can give you a false proof, that is limiting. Okay, we can't do everything we want using that this notion, and therefore we're going to go into a new notion of soundness, which is what we call arguments or computational soundness. And we're going to relax the prover and say an all-powerful prover may be able to cheat, but the guarantee we give, hey Tony, is that a computationally bounded prover cannot cheat. Okay, that's going to be the guarantee we get, and we'll see once we relax the soundness requirement to a requirement that's only computational sound, then we'll be able to get a lot more, and kind of the life will kind of open for us, and we're going to have a lot of new kind of constructions and things that we were unable to do information theoretically. So this is the plan for today. Questions before we start? I haven't seen you guys in a while, so it's good to see you. A lot of things changed since the last time I've seen you. I'm probably going to be a bit distracted today, so I'm sorry. Okay, let's start. So no questions? Okay, so let's start with PCPs. What are probabilistically checkable proofs? So the idea of probabilistically checkable proofs is to take a proof, like a classical proof. Think of NP. In NP, we have an instance X and a witness. This witness is like a proof for X being in the language. To verify this proof, you need to read the entire thing and do some computation, like this verification circuit, that checks that X and W is in the relation. There's a circuit that checks this. Okay, what is the idea of a probabilistically checkable proof? The idea here, what we want is to take this proof and convert it into a new proof. It may be larger, actually, than the original proof. So maybe, the original proof was of size m. Let's say the instance of size n. This may be of size much bigger. Still, we want it to be polynomial in n and m. But now, so we just made it bigger. So what's good about it? So what's nice about this proof is the idea is you don't actually have to read all of it to check it. And that's weird. So the idea here, the proof may be a little longer, polynomially longer, but you only need to read a few locations to check that it's valid. So to verify, often PCPs are denoted by pi. To verify a PCP proof, given X, all the verifier needs to do is query. He doesn't actually need to read these things. He queries a few locations, a few bits, checks a few bits of the proof, and then applies a verification circuit that depends only on these bits. Okay, and importantly, the bits he chooses are random. The prover doesn't know, otherwise it's like shrinking. If he knew, the prover knew, the verifier is going to only check in bits 17, 22, and 25, then he would just give you, it's like you'll have a succinct witness. And of course, we can't take arbitrary witness and just make them succinct. We don't believe that's possible. Yeah?
So is the PCP then only used for m is much greater than n?
Okay, so the question was, is a PCP used if m is much greater than n? And the answer is no. Actually, we can think of it, we can even use it where m, the length of w, is n to the epsilon. Okay, even less than n to the epsilon, even n to the little o of n. Now this will still be polynomial in n. So actually, you took the proof and make it actually more than polynomially larger because it's polynomial in n and m. And if the proof here is smaller, is n to the little o of 1, then this is poly n. It's actually more than polynomial bigger. But, so you're saying, what did we gain? We took a short proof, made it so much bigger. What did we gain? And what we gained is the hope is that you can query this. The verifier can query this in very, very few locations. Read only very, very few bits of this proof.
Okay, you get a but then does the verifier also have to read X then?
Yeah, the verifier, all of X. So yes, good. So the question, that's a good question. So the question was, does the verifier have to read all of X? And because I said he only needs to read a few locations in the proof, does he need to read all of X? And a priori, of course he needs to read all of X, because even if there's one bit in X that he doesn't read, what if that bit is, it's actually what the sentence is, what the statement is. The prover needs to know, what am I reading? What are you proving to me? But there are extensions called PCP of proximity, which I'm not going to get into in this class, where actually the verifier also doesn't read all of X, but the guarantee is not that X is in the language. The guarantee is that it's the oracle that is given to the verifier, there is something close to it that's in the language. So there is a notion of extension of this notion of the PCP where the verifier doesn't even need to read all of X. The guarantees there are not very easy to state, but it's a very useful notion. Actually, it's used a lot. It's called PCPs of proximity. Okay. So that's what we're going to do today. Okay, and let me just mention, before even we start the formal thing, let me just say, this is really an amazing line of work. Today we know how to take any witness, convert it to a probabilistically checkable one, that the verifier only reads 3 bits. 3 bits of this proof, and is convinced with constant probability. 7/8 is the parameter. And then if you want more, of course, you repeat. But even with just 3 bits, you get some soundness. And that's really amazing. So we're not going to see the 3-bit proof, but we're going to see a polylog n proof. So what we're going to show, what the construction we're going to see today, is how to go from a witness to a probabilistically checkable one, that the verifier only needs to read polylog n of these bits and verify. And to go to the constant, there's additional tricks of recursion and so on that one needs to do to get there. But we're not going to cover that part. OK, ready to roll sleeves? OK, let's. OK, so let me just define the complexity class. People often think of it as a complexity class, even though for us, because this is more of a proof system cryptography class, we always want efficiency. We don't care just about complexity. We want to say that actually we can take any witness and efficiently convert it. It's not just about existence. We want to actually use these things. And let me just jump ahead and say that these things are used. It's not just a theoretical, even though everything we've seen so far in the class is like very just beautiful mathematically. It seems very, kind of low, like very very far from practice, but actually it's not. All these things that I've shown you so far, that you've seen so far, are things that actually are used, and and the PCP as well. All this machinery are things that's used, so we actually do care about efficiency. But let me first kind of define it as a complexity class. So we define the complexity class PCP, C for completeness parameter, S for soundness parameter, R for randomness parameter, and Q for query parameter. So this is a class. This is the class of all languages L that have a probabilistically checkable proof, but I'll explain exactly what I mean. Okay, so actually let me say, okay, these are all the, let me write it formally, for which these are all the languages L, such that there exists a PPT, a probabilistic polynomial time verifier. Actually, it's a PPT oracle machine, because it takes the PCP as an oracle machine, V, such that, okay, So the completeness, here's the condition. The completeness says that for every x in the language, there exists a PCP pi such that the probability that V, the verifier, given Oracle access to this PCP pi and input the instance, so for every instance, there exists a PCP so that the verifier will accept, it will output 1 with probability at least C. That's the completeness parameter. For us, the PCP we'll see will have completeness parameter 1. Okay, so we'll see. So we want to say that a class, that a language L has such a PCP if there's a verifier V, a efficient verifier, it takes Oracle access. So if X is in the language, there exists a PCP. So that the verifier with Oracle access to this PCP, given this input, outputs 1 with probability C, yes?
Maybe I'm jumping the gun a bit, but what does the Oracle look like? Like, what are the inputs and outputs?
Okay, good. So this, okay. Oh, good. No, you're not jumping. So good question. So this pi, you should think of it as a string. It has bits, B1, or maybe I call it pi 1, pi 2, up to pi, I don't know, n. And the verifier can ask, give me like pi 1, give me pi 2, give me pi 3. So it just has Oracle queries. He can query this string. Okay, that's what Oracle, it's not really, don't think of it as a function. He has Oracle access to the string, and he can just ask for specific bits from the string. Great question, thank you. Okay, good. And the soundness guarantee says that for every x that's not in the language, any guesses, by the way? What would you, okay, so you need to define a PCP here. How would you define soundness? Yeah?
I guess for all pi prime, the probability that a verifier with Oracle access to pi prime accepts x is at most s.
Wonderful. Exactly. You want to say that for every pi star, this is often how we denote bad things, but pi prime will do too. For every bad, now there's a cheating prover. He tries to fool the verifier. He cannot. So for no matter what he tries to give him, the verifier will reject him with probability or will accept probability smaller than S. That's the soundness guarantee. Okay, and ideally we want to push the completeness to 1, the soundness to 0. Great. And then the complexity is, now we want to say in terms of complexity, now we'll go to the V uses R bits of randomness and Q Oracle calls. And moreover, we'll see this is important for us. This is often in the definition, though not always, but often this is part of the definition. Q non-adaptive. What do I mean by non-adaptive? What I mean is the way V works, he gets input X. He gets input X. He then chooses kind of I1 up to IQ locations in the PCP. Okay, so here's the V. V, he doesn't even look at the Oracle yet. He has an input X. He first computes Q locations. He then goes to the Oracle, asks these Q locations, and then, so V1 just decides these locations, and then V2. So you can think of V as being like V1 and V2. V1 doesn't look at his Oracle. He just looks as an input, and using randomness, chooses Q locations. And then V2, kind of just given X, I1 up to IQ, and pi I1 up to pi IQ, decides if to accept or reject. Okay, so this is how you should think of the verifier. The verifier has access to the proof pi, but what he does, because a more general verifier will have X, decide on location, first location treat I1, look at pi 1, then, interesting, okay. In that case, I want to see location I2. I get pi I2, interesting. Given pi I2, I want to see location. That would be an adaptive verifier, okay? But often in the PCP literature, when we define PCP, we require the verifier to be non-adaptive. And this non-adaptivity is kind of is a property that we like for applications, and we'll see that today. Why, an example for why, when we'll construct succinct arguments, we'll use the fact that it's non-adaptive. But let me just say, most PCPs, all PCPs I know are non-adaptive. Maybe there are other. Was that your question? Yeah. So there may exist. I'm not, I'm not. I didn't do a full literature search, but the PCPs that are, the most common ones that we talk about are all non-adaptive. Yeah.
Did V get to know what capital N is?
Yeah. So V, yes. V knows, yeah. So V, very good question. Let me repeat for the video. So the question was, does V know what capital N is? So the answer is yes. And V knows the language. So he knows what small n is. Well, he got small n. He knows small n. The language has, there's M. So V gets small n, so he knows what n is. The language is associated with a witness size, M of n. So he knows that because he knows n, so he knows the witness size. And the PCP itself is associated with n, which is, you can think of it this way. So the answer is yes, these are kind of fixed. These M and N are fixed parameters that are defined by the PCPs, and the prover knows them. The verifier, the prover, they all, yeah. Yes?
Do we gain or lose something to make V adaptive?
Yes, good. So the question is, do we lose something? And the answer is we do. Okay, so what do we lose and what do we gain is your question. What we lose is for application. So when we'll go to, in the second part of today's class, we're going to construct succinct arguments, and we're going to construct them from PCPs. And you'll see that if our PCP is adaptive, this becomes a problem. So we do gain. Now you're saying, what do we lose? And so we do lose. Sorry, we do lose if we make it adaptive. Now you're saying, but maybe we gain something. Maybe we construct PCPs that are much better if you make them adaptive. And I don't think so, but I'm not sure. Maybe one can actually argue that you don't gain anything, but I haven't thought about it. But it's not something that, making it non-adaptive, is that, for all we know, is not a price. It's just, our PCPs happen to be that way. Yeah?
Is there a version where you choose the instance it had on X?
Good. Very, very good question. So I think maybe I misunderstood, but maybe your question was, is it clear that these have to depend on X? Can they even not depend on X? And the answer is yes. Actually, in the PCPs we'll see, they don't depend on X. Okay, the PCPs we know, actually, they only depend on, n, on the instance size, or big N. But they don't actually depend on the instance. And the PCP I'll construct today, you'll see that. So we'll get back to that. That's really, really great questions. Yeah?
High level, how does that work? Because you think that if the prover knows what indices you're going to query in advance, you could construct a fixed.
Of course. Great. Wow, guys, you're really lifting me up. This is great. Thank you. Yeah, 100%. So what you're saying is, of course, if the prover knew the locations you're querying, he will cheat. The thing is, these locations are random. The prover doesn't know what they are. They just don't depend on X.
Oh, okay.
Okay, but they come from a distribution. It's very important. If these were deterministic, there's no way. If you can do a PCP where these are deterministic, it's like you took NP and you just made it n time much smaller. We don't believe that can happen. No, there's no way we believe you can construct PCPs for which the query distribution is deterministic. It's just fixed. This has to come from a distribution. But the question is, does this distribution depend on X, or does it only depend on the parameter n? And in what we'll see, it actually only depends on n. It doesn't depend on X. So that's what we'll see in a minute. Great question, guys. Any more questions before we? Yeah?
So V allows you randomness in V1 and V2, or do we really only care about the randomness of V1?
So, okay, good. So actually, V1, you can think of, usually V1 is randomized and V2 is deterministic. So you can think of it that way, that V1 is randomized, V2 is deterministic. Okay. Great. So now, let me tell you what we know and what we're going to construct. So here's what we're going to prove today. Here is a theorem that we're going to prove, that PCP with a, let's say, completeness 1. I'll put soundness half. We can get smaller, any constant smaller, but I'll just put half because by repetition, it doesn't really matter. You can get a PCP where the query complexity is, so, okay, we can get a PCP with polylog n query complexity and polylog n, polylog n randomness complexity and query complexity for all of NP. That's what we're going to see today. So we're going to see how, for any NP language, we can construct a PCP where the verifier, the amount of randomness he uses, is polylog n bits of randomness and polylog n queries. And then we get completeness 1 and soundness half. Yeah, Tina.
Just so I totally understand, like, this is not the usual parameter regime PCPs, right? Like, usually you want the proof, you want the randomness complexity to be O of log, so the proof is actually polynomial, is that right?
Right. Yeah. So you're right. So often, okay, you're right. The way I wrote it here, okay, why do people care about randomness complexity? One can say, well, who cares about the randomness complexity? And usually the way I define PCP, and that's what I said as a complexity theory, this is how it's defined. If the verifier has only log n bits or order log n bits of randomness, then it means that the PCP is only poly n size. Because, look, go over all the poly n, all the log n bits of random. There's only n of them. So that's as much as you can kind of query. So that means the PCP is a poly size, and that's what we care about. Okay. For me, I'm going to care about, so actually for me, I'm going to add a requirement. Actually, I didn't write it here because it's usually not defined, but I can add a requirement that says this, I'll add it here in tiny. This is a requirement that we add in cryptography. Often, what I'm writing now is not added in the definitions, but let me write another cryptography, that given for every x in, or x, for every x in L and witness, if it has a witness, W, okay, so suppose this is a language in n time, I don't know, NP or n time t, so it has some witness. I want it to be the case that given x and W, you can efficiently compute pi. So not only there exists pi of poly n size, you can actually efficiently compute it. And because I require efficient computing, I actually don't care anymore so much about the randomness, the number of randomness bits. But yeah, that's a very good point. Thank you. Guys, thank you for the questions. This is great. Okay, so that's what I'm going to prove, even though, let me just mention, what is known is you can make this order log n, and you can make this 3. Okay, so it's really remarkable. If you think about it, wow, you can take any proof. So you know how, I don't know, take Fermat's last theorem, take the hardest proof that we know in mathematics. You know, one can write them in a probabilistically checkable way. They can just take 3 bits and verify. And if you're not happy with probability half, repeat it as many times as you want. You want to be sure that he can cheat with probability only 1 over 2 to the 500, repeat it 500 times. And each one, it's like a very simple check. It depends on 3 bits. So it's really remarkable.
No, never mind. Sorry. It's like n choose 3 is probably way too big, but I guess it doesn't really matter to I don't have like all possible.
Oh, you're saying it's too big because for theory, for practice. Yeah, but we're still in theory land. Yeah. In practice, these PCPs, you want them to be like linear. That's the ideal, the quasi-linear. Even if they're quadratic, people don't like them. You really want linear, quasi-linear PCPs for practice. But for here, poly is fantastic. We're not the, let us stay on the cloud a little bit. Okay, so let's construct this. Ready? Okay, so we have the 3, but we're going to construct for the polylog. And what actually, here's what's amazing. You actually already know how to construct a PCP. You just don't know that you know. And how do you construct a PCP? It's really only the GKR protocol. That's it. So you can unfold GKR, and I'm going to show you exactly how to make it a PCP. So to do that, but before, and I'll recall the GKR in a second on that board, but to do that, let's first, so I want to say any language has a PCP. Let's focus on 3-sat. Okay, so 3-sat is an NP-complete language. Let's just construct a PCP for 3-sat. And what's nice about 3-sat is that, I mean, any NP language you can convert to 3-sat, so it's nice, any NP language, is that you have a circuit, a verification circuit. So a circuit verifying, so you can think of it given W, verifying that it's a valid witness, of very small depth, okay, polylog n depth. And this is important because if you remember the GKR protocol, which we're going to use to construct this PCP, kind of the communication complexity grows with the depth. So we want the depth of the circuit to be small. But any NP language you can convert into a 3-sat, and 3-sat has, actually it's like the depth of 3-sat is like actually only 2, but like you need to do, little ORs and then one big AND. But if you remember GKR, we wanted fan in 2. So once you have fan in 2, it's like order log. Okay, so this is depth. You can think of it as being a like log n, or I'm okay with polylog n. It doesn't matter. The point is it's small. And the reason why I write also polylog is because it's actually log. However, this circuit is also any kind of, the circuit is, and this I'm not going to get into, but it's log space uniform. And now you can consider the circuit, change it a little bit, the way Rachel taught you 2 weeks ago. If you don't remember, it's okay. You can take it as a black box. You can assume that this circuit, by kind of looking at a universal version of it, you can assume that it has, like the gates add I and multi I are efficiently computable. And that's what we'll need. So we can, if you don't remember things from 2 weeks ago, it's okay. I'll remind you what add I and multi is in a second. But you take any 3-sat, you can convert it, or convert it to 3CNF. So now given a witness, you just check that it verifies, hi, hello, hey, wow, all my kids coming in. Okay, so you just, we're talking about how to construct PCPs from GKR right now. So what we're proving is that we're going to show how you can take any NP language. In particular, we're focusing on 3-sat. And we're going to show how you can convert 3-sat into a PCP where the query complexity is polylog n. So convert into a PCP, the verifier needs to query only polylog n locations. We know you can go all the way down to 3, but we're not, today we're going to show polylog. This is the randomness complexity. This is the query complexity. We're focusing on completeness 1, soundness half. Okay, so we're going to now construct the PCP. And before we construct the PCP essentially uses GKR. So let me first on this board remind you quickly what GKR looks like, because we're going to use it to construct the PCP. Okay, your cameraman, it's okay to move? Yeah, okay, no okay. Good. So let's just recall the GKR. How does it work? We have a circuit. There's an input W. We're going to think of W here as the satisfying assignment. Okay. Remember, in the GKR, we assume the verifier has W in his hand, the input in his hand. Here he doesn't. W is going to be the witness for the satisfying assignment, but that's okay. Now, here's what. So I'm going to construct the PCP proof. Okay. I have my witness, my satisfying assignment. I'm going to construct a probabilistic check. I'm going to convert W into a PCP, into a probabilistic checkable proof. Okay, here's how I do it. I look at the circuit that checks that W. Actually, you can, if you want to think of it as completely uniform, you can think of having X and W. So X and W, and it checks that kind of phi, X, which is phi, and it checks that phi of W is 1. Okay, this is a log space uniform circuit, and okay, now what do I do? So here's me. I know W. We both know the 3-set formula. What I do, and we assume that this circuit is has addition gates and multiplication gates. What I do, for every layer, I compute the values of the layer. Okay, so I compute for every layer. Remember, I have VI. I assume every layer, let's say, has size. Let's say the same size without loss of generality. We said size S. We called it S. So each layer has S wires. And we compute all these wires for every layer I. We think of this wire as going from H to M to 0, 1. So H is some set, and we assume that H to the M is S. Okay, so we just encode these S wires in a kind of cube, n-dimensional cube of size H, and we just write all the values of the wires. Okay? And then what we do, we look at the extension V tilde, which extends to a field F to the M to F. And this is kind of the low degree extension. So we take any F that contains the set H, and we extend VI via the low degree extension. So these are things we covered. Okay, now is the first time you remember when we taught GKR, I told you, okay, why not do 0, 1 to the M? 0 to the log n, it's much natural to think of binary representation of S as opposed to this H to the M, which is what H. And I told you, often we like parameters. We like to think of H as log n. Log n, and M is log n over log n. And if you'll see, H to the M becomes n because you can think of H, so H to the M is log n to the m, but log n is just like 2 log n to the m, and the log n cancels out, so you have 2 to the log n. So you have, I did everything. Everything is S, sorry. S, the n here is S. S, S, S. So you have S. Now, remember I told you, we'll need this set of parameters as opposed to the 0, 1. It's natural to think of H as 0, 1 and M as log n. That's much more natural. We're used as computer science to think in binary. Now we're thinking of like log S. It's like, really? How annoying can you be? And the reason is it's for this. Now we need it. Why? Now we take F that is going to be, it's going to be extension of size poly log S. Okay? We'll see the poly will need to be big enough. We'll talk about it in a second. But the field we don't want more than poly log S, and the reason is we want F to the m to be poly S. Okay, so we know that H to the m is S if F is only poly bigger, then we have this is poly S. Okay, and that's important for us. Okay, note if H was just 0, 1, so the size of H was 2, we couldn't keep F poly in 2. We couldn't keep F constant. You'll see F will need to grow with M. F, so for soundness, MF will need to be bigger than M times H. Actually, there's also D that will come in. It's significantly bigger. So if we take H to be 2, we'll need to take F to be at least log n, and then we'll have F to them is log n to the power of log n. That's super poly. And I want F to them to be poly. Okay. So we do this. So what is the PCP? The PCP, so actually, I'll write there the PCP, but now let's just finish recalling the GKR. So what does the verifier do in the GKR, the prover do in the GKR? He computes all these low degree extensions, and then the GKR consists of D phases going from the output layer to the input layer, where in each phase we run 2 sum check protocols in parallel, where the verifier uses the same randomness, And what the subject protocol does is it reduces from checking 2 values here to reducing checking 2 values in the layer below. And we kind of go from checking until we get to the input, and the input the verifier can check on his own. That's the idea. Okay? Okay, now let's just recall, in a subject protocol here, each subject protocol, if you remember, maybe you don't, it's not, the details are not so important right now, but it's kind of, you go from VI in the extension, which is, let's say, VI tilde of some Z, and you write it as this is kind of sum of points in H to the M, because that's the definition of extension, times some chi P Z. This is the function that checks equality. Again, it's not important, but what's important to me to show is that, and then you do sum over P W1, W2 in H of M, and you convert VI to either kind of if this is a plus gate, you convert it to the plus of the wires below. If it's a multiplication, you check the multiplication. So in other words, what this is, or I should say what this is, let me just open this. What is VIP? If it's an add, PW1, W2. So if point P is this just the addition of the 2 wires below, then you replace P with W1 with VI minus 1 W1 plus VI minus 1 W2. And plus, if it was not an AND gate, if it's a mult gate, then you replace it with the multiplication of VI minus 1 W1 times VI minus 1 W2. So just right, the idea was, and all this is times this chi P Z. But again, how do we go from layer I to 1 layer below? We take that element in the extension. We think of it as a sum. That's the definition of low-degree extension. It's sum of the elements in the circuit itself with some function, with some weight. And now we look at the value. What is the value of this gate? Well, if it's an AND gate, it's the sum of the 2 children. And if it's a mult gate, it should be the multiplication of the 2 children. And so add I just outputs 1 if W1, W2 are the children of P, 0 otherwise. Similarly, mult. And but we do everything in the extension. We look at everything in the extension because we want to think of it as a polynomial. And once we have these are all polynomials, then this is just a sum check. Okay, and we saw a sum check how to do it efficiently. So now the point is GKR consists of only these 2D sum checks. So now let me go to my PCP. Where is this? So here's our PCP. Essentially, my PCP is just GKR, but opened up, completely unraveled. So, okay, so here's my PCP. I have my X and W. Here's what I do. I'm going to compute all the VI tilde, the extension of the values of all the gates in each wire for every Z. For every Z and F to the M. It's important, all this is going to be part of the PCP. So if F to the M is more than polynomial, my PCP is super polynomial. Okay, so F to the M has to be polynomial. This is a ready size polynomial. Yeah?
Do we still have a restriction statement to have that T log restriction?
Again, sorry?
We should have that restriction on the statement X to have that T log space. Because for GKR.
Oh, yeah. Okay, good. Yes, so For GKR, we had a restriction that the circuit, to do GKR, we said GKR is proving that bounded depth circuit and input x equals y. And we had a restriction that the circuit has to be bounded space uniform. Or in other words, we needed to ensure that add I and multi, this extended and I and extended multi, are computed efficiently. 3-SAT has that property. Okay? I did go into the details, but the 3-SAT it's a very uniform, given a phi and x, it's very uniform to check. It is a log space uniform, and then we can convert it, as Rachel did 2 weeks ago, to kind of one that has, by increasing the depth by polyfactors, so keeping it polylog, you can make at tilde and multi be efficiently computable. So yeah, great. That's a very good question. So yes. Good. So this is going to be part of the PCP, but that's not all. By the way, we should also give this. We give this for every I from the input layer, 0, 1, up to D. This is output. And this is the input layer. We have to give in the input layer because the poor verifier doesn't have W. So he doesn't have actually the input. Before in GKR, he had the input. Here, he doesn't have the input. But we're going to give him the low degree extension of this W. OK, good. Now, so I'm the verifier. What do? I need to verify the sum checks. Who do I interact with sum checks? I'll put all the possible answers in the oracle. So now we do 2D sum checks. So for every possible, for every I, and for every Z, in the GKR protocol, we may need to do a sum check. Because in the sum check protocol, in the GKR, how does it look like? The verifier first decides, prove the output layer is correct. Let's say the Z is fixed, fine. Then he chooses randomness in the sum check. It reduces to checking V D minus 1 in a random Z. The Z is determined by the random coins of the verifier. So which Z do I put? And I want to show a sum check for every possible Z. So for every possible I, for every possible Z, I'm going to put in the PCP a sum check. So I'm going to give a sum check. I'm going to add kind of all the possible transcript for a sum check corresponding to VI, which VIZ, or maybe to VI equals VI tilde Z. So for every I and Z, I'm going to give a sum check with respect to randomness R from the verifier. So for every I, for every Z, and for any randomness R of the verifier. Now, how much randomness does the verifier use in a sum check protocol? So remember, the sum check is sum over h to the 3m kind of variables. Okay, it's sum over P, W1, W2, all of them in h to the m. So the R is going to be for every R in f to the 3m. Because in the sum check protocol, what you do is every single h, every single kind of, you have 3m variables. Every one you give a random field element to kind of get rid of one of the sums. So the verifier will choose kind of R1 up to R3m. So 3m field elements. So for every possible, for every R, I'm going to actually give you the transcript. So now I know I'm going to give you the entire transcript. Okay? But here's the thing. So I'm going to have a sum check for all of them. And now the verifier, but we need to be careful. We don't just give for every R a sum check. If I knew R, I would cheat. So what I mean here is for every sum check, for every VI, for every R, for every R1, I'm going to give all the outputs for R1, like all the kind of answers of the sum check for R1. Then for each one of them, for every R2, I give all the possible answers. So no repetition. You can't have two different elements. You can't have one value if you had R1, R2, but later different Rs, or R1 or R2. For every possible partial transcript, you give a value. That's what the PCP has in it. Okay, so for every, I should say, so for every I, for every Z, and for every, maybe I should write it as R1 up to R3M, I have a transcript. All the I should have all partial transcripts of sum check with respect to Vi equals Vz and randomness, R1 up to Rj for every j. Okay, between, 1 and 3m. Okay, so for every R1, I will say, what would be my answer? So now I have f to the m answers. For every one of these answers, for every R2, I'm going to tell you what is the answer. For every, sorry, I said it wrong. For every R1, I would give you all the answer. I have f. Each one is one field. So for every R1, I'll tell you the answer. That's f options, because there are f options for R1. And then out of these f, for each of these f's, for every R2, I'm going to give you what the prover will send. That's f squared. And then for each of these, I'm going to give you R3. So really what this PCP, for every VI, for every such VI, or for every kind of VIZ, for every possible R1, I'm going to give you, this is over R1, I'm going to give you the possible answers in the sum check protocol. Like if the prover in the if the verifier in the sum check protocol, the first randomness was this R1, this R1, this R1, I'm going to write all of these in the PCP. And then for each R1, every possible R2, I'm going to write my answers. And then for each R1, R2, for every possible R3, I'm going to write my answers. It seems like an exponential tree, and it is an exponential tree. But the depth is so small. So this is a huge tree, but this tree is only of size f to the m, or to the 3m, sorry, which is polynomial. It's s to the third. And you're right that this is not good enough for practice, but then there's a lot of optimizations in the GKR that make it quasi-linear and today even linear. So you can actually optimize this to get linear time, or quasi-linear as a PCP. But for now, we don't care about these. A polynomial is good enough for us. Okay, so for every I and for every Z, we give this tree. That's the PCP. That's it. Okay, so again, yeah?
Doesn't the sum check protocol rely on the fact that f is big?
Good. Fantastic. You're like, wait, that's a problem. If I require f to be small, do we even get soundness? That's a great question. So the answer is barely, but yes. So let's see. What is the soundness that we get? For it to be sound, each sum check, so so let's talk about soundness. Maybe I'll put it here. Let's talk about soundness here for a second, because you raised but you know what, actually, before we talk about soundness, I'll jump to soundness. You have a very good point. We'll talk about soundness, but just to make sure the construction is clear. Okay, so let me just reiterate one last time. I'm a PCP prover. I want to convince you guys that I have a satisfying assignment to a 3-set formula. I have my W. What I do, I construct low-degree extension of my W, my witness. But also, I have this entire circuit that verifies this witness. And I'm going to construct a low-degree extension of each and every layer in this circuit. Now, the way I wrote it, actually, I will construct a low-degree extension of X and W. That's kind of, if I think of the input as X and W, I need to construct a low-degree extension of both. But the verifier knows X. So if I construct a low-degree extension of W, he himself can construct a low-degree extension of X and W together. So in the PCP, because I don't want to, in the PCP, I don't want to put X in there. The verifier has X. And if I have the freedom to put X in there and you don't read it, then I can put the wrong X. So I'm just going to put V0 is just going to be of the witness. I'm going to think of X as fixed. So I'm just going to construct the low-degree extension of W. And then I'm going to construct the low-degree extension of each and every layer of the circuit. And I'm going to go for every layer and for every Z. I'm going to construct all the possible prover messages in the sum check protocol. Now, because the randomness, the options for the number of possible random bits from the verifier is only f to the 3m, because there's 3m variables, and f is the field, so it's only f to the 3m. Then this tree is only going to be of size f to the 3m, so it's not too bad. And I put all of them. I put all the possible sum checks in there. So, sorry, it's f to the 3m. For every, I have this size for every I and for every z. Okay, so for every I is only d, this is small, and z is another f to them, I pay, fine. So f to the 4m. Okay, so for every z and for every I have this sum check. Now that's the PCP. But now what does the verifier do? What does V? I need to define, I told you how to construct this pi efficiently, and but what does V do? So what V does, he says, I'm going to pretend that I'm interacting with a GKR prover. So he says, look, what is the output? He's going to read the output, VD. And he's going to expect a 1. If he sees a 0, so that's one query. I'm going to read the output. It's 1, good, I'm happy. Okay. Now he's going to go from verifying D to verifying D minus 1, D minus 2, D minus 3. Now, he wants to talk to a prover. He says, OK, here's my randomness, my first message in the sum check. Give me back something. OK, so this is the prover. The prover is fixed in the PCP. OK, so he gets back an answer. Good. Now, here, these at the end, this defines Vi minus 1Z. This should be all kind of elements in V minus 1Z. Now, actually here, what you have here is at the end of the GKR protocol, you're left with two V's, right? So if you verify here, you'll have like, at the end, you'll have like V, I don't know, 0 and Z0 and Z1. You know, you need to verify 2 points because we did 2 sum check all the ways. So fine, he sees these 2. He checks, there's these. He checks that they're equal. This is only 1. Okay, so we're giving him all the low degree extension of Vi minus 1. He checks it, oh yeah, this corresponds, this corresponds. This is just to ensure that he doesn't put different ones in different, here he may, and in this branch he may put the value of Z0 to be something, and in this branch he may put the value of Z0 to be something else. That's not good for us. So we just check, because he put aside all the low degree extensions. So we check that it's equal to what he gave us. And we continue with that. Okay? One second. Actually, I'm not sure. Maybe what I said is incorrect. I'm not actually sure that this is a problem. Even if he gives us different, let me think about it for a second. Yeah, actually, I'm not even sure that we can just put the sum checks. Even if he gives us a, no, okay. Yeah, I want to say, even if he gives us in this branch and this branch different things, why do we care? It's like we ran the sum check, and the sum check is sound. But we do care a little bit, because then in the next round, which, let me think. You know what, I'm not actually, what?
My understanding is that you sort of just lay out the whole randomness of the verifier, right? And then the verified sort of actual interaction with the prover just like follows each other.
Exactly. You lay out all the verifiers. So yeah. So I don't think actually you need to give these specific. You can just give for every vi tilde, you give, but it's the same because you give for every vi tilde. So actually, I think these two are the same. So okay, I guess what I said is, these can be, maybe vi minus 1 of z0 appears here and it appears here, and they're different. Are we worried? We're not really worried, because it's like, you think of it, it interacts with the prover. The cheating prover may give him different z here and different z here. But later, the point is later you'll have in vi minus 1, you'll just continue. So actually, you just need to give, but really, I think the two are equivalent, so it doesn't really matter. Okay, so this is the PCP, and that's how you verify. And at the end of the GKR, the verifier needs to read the input. He needs to check the input in some locations. He doesn't have the input. But he does, because we gave him the low degree extension of W. So once he has the low degree extension of W, he can compute anything. So the verifier needs to compute a low degree extension of X and W, but any point in the low degree extension of X and W is a point in the low degree is a sum of points in the low degree extension of X and point in the low degree extension of W. So every point in the low degree extension of X and W, you can write as a weighted sum of a point in the low degree extension of X and a point in the low degree extension of W. So, once he needs to read the point in the low degree extension of W, he has it here. So that's all the verifier does. So it's interesting, this PCP, as if he's talking to the prover, but the prover is sitting in the sky, in the PCP. The prover strategy just kind of opened up in the Oracle. Okay? Okay, great. So now, any questions before we talk about soundness? Yeah?
So in this protocol, the verifier first needs to check that the low degree extension of the input is correct, and then simulate the.
So, right. So, okay, good question. The verifier, great question. The verifier needs to check also that all these things are actually low degree extension. Okay, so what if I said here, you put vi tilde z. How do I know that you actually put a low degree extension? Maybe you put a very high degree polynomial there. Maybe you just put an arbitrary truth table of size f to the n. That would be problematic. So you're totally right. The verifier, so let me write what the verifier does maybe before the soundness. Yeah, so let me actually write it. Okay, so the verifier, okay, he runs, first thing he does, he runs V of GKR with its oracle. Okay, so he runs just the GKR, but he thinks of kind of the oracle part as kind of the prover he's talking with. And the other thing he needs to do is he needs to check that for every I, vi tilde is of low degree, is
Doesn't the original verify from GKR do that? Like, again, doesn't the soundness of GKR just rely on it being low degree?
Yeah, what you're saying is that if, you're right, so what you're saying is okay, what you're saying is if he gave vi tilde that was high degree, then you're saying the GKR would fail. You would be rejected by the GKR.
Should be, otherwise it doesn't work, right? Like,
It should be rejected by the GKR. I think you may be right, but actually I'm not 100% sure now. Yeah?
Is the issue here that VI is of high degree but still agreeing with VI of low degree?
Yeah, so here's the concern. Here's the concern. The concern is we want to make sure that the verifier is behaving like the, we want to make sure that this VI tilde is of low degree. Why? Sorry, 1 second. Yeah, actually, I don't think we need to check that VI tilde is a low degree. Because I agree that we need to check that VI tilde is a low degree. But I think GKR checks that the VI tilde is a low degree. So I actually don't want to recheck it. So all I want to do here, I think GKR tests it for you. So we're convinced that the GKR is sound. Let's not recall why it's sound. But let's remember we learned that it's sound. So GKR is good. Now what are we doing? Essentially what we're saying is, verifier, I'm giving you all the possible answers of, what is the prover? The prover is a tree. You can think, what is a cheating prover? A cheating prover for every possible, for every possible question, he gives you an answer. For every question, he gives you an answer. That's what it does. So now you're saying, look, I'm going to give you the tree. Now, in general, this tree is really, really big. And even in GKR, if you give the entire, if you just open, like GKR has D rounds of sum check. If you just open the sum check, it will be terrible. However, GKR has this property that it's kind of memoryless. What do I mean by memoryless? You can compute the first sum check. Then you don't care what happened before. All you care is what is VI minus 1 that you got. And you check those. So now I'm saying, so you know what, actually, let's think about this. First of all, we can say, open GKR to a huge tree. Okay, any prover, and this is true in general. If you had any interactive proof, you can think of a prover, write all the possible answers. Like think of its kind of strategy as a huge, huge tree. Write the tree. Now, of course, you get soundness. You interact with the prover. What's the difference? Okay, you can do that with GKR. But, of course, if you do this huge tree, it's going to be gigantic because GKR consists of D kind of sub-protocols. Each one is a sum check. So now if you think of like a D to Kalai, then you'll be too big. But I'm saying we don't need to because GKR has a property that actually it consists of this sub-protocol. And then all you need to remember, you don't need to remember which branch you're on here. All you need to remember is what are the values here. That's all you need to remember. So there's no point in repeating. It's like you're repeating the tree for no reason. So all you need, there's a way to open kind of this prover in a more efficient way. So by not giving you the entire tree and giving you kind of a more efficient kind of opening where all the VI minus 1 Z, I'm going to say, okay, forget about it. Let's just go from VI minus 1 Z and continue. Why do you need to repeat this kind of tree 100 times? But you can go from here to kind of simulating an entire GKR prover. Yeah?
So if I understand correctly, you're just saying like actually the tree of GKR is such that most of the parts are sort of copied, right? And so you don't need to repeat the copies, you can just look it up. Right?
Exactly. 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 Actually, in some sense, we're restricting the prover here more than he's restricted in GKR. Exactly, because in GKR, he can be, you know what, I'm going to remember the R's if he's cheating. And based on these R's, I'm going to give you a different strategy. Whatever. Here, we're not even letting him do that. We're telling, look, you tell me what you are here. From here now, you forget the R's. From VI minus 1, what's your strategy? And now you forget, from here, what is your strategy? So we're really just doing GKR. Now, you're right that the VI minus 1 tilde do need to be of low degree. But the GKR tests it for you. So you don't need to do it on your own. But you're right. It's confusing a little bit because if anyone is familiar with the PCP literature, there's always a low-degree test in it. So it's kind of interesting. This kind of is hidden within the GKR protocol.
So this kind of transformation holds not only for GKR, as long as there is an efficient way to change the prover into a sequence that the verifier know where to query, it will give you a sequence.
Exactly. So yeah, this proof holds. It's not specific to GKR. It's kind of, you can take any succinct protocol and interactive protocol and lay it open. However, let me just mention, we have very few, actually kind of 2 examples of succinct protocols. So it's not like you can take any of your choice. Yeah, any, but we don't have much choice. So, coming up with these succinct interactive proofs is a super interesting question. I'll talk a little bit more about this after we do the analysis of the PCP. Okay, so great. Any questions before we move to soundness? Okay, so let's talk about soundness. And the question that was raised, which was a great question, is, wait, F needs to be big to get soundness. So let's really understand what the size of F needs to be. So to get soundness, we do 2D sum check protocols. Each sum check protocol needs to be pretty sound because it's enough that you cheat on one of them and we're dead, right? So now each sum check protocol, this is just recall that each sum check protocol has soundness, which is H over F times M, the number of variables, but for us it's 3M because we have 3M variables. Okay, this is just the each sum check protocol. Now for us, so you can cheat, but with this probability. Now for us, we have 2D. D is polylog n, like the depth of the circuit. So for us, our soundness is, I'm just doing a union bound. So to cheat, there needs to be at least kind of one sum check protocol for which you cheated on. So you get by union bound. So we have 2D sum checks. And then therefore the soundness is 2D times 3M H divided by F. So now if we want soundness half, let's say, which is what we want, after that you can repeat to increase the soundness. All we need is that F, so if we want this to be smaller than half, then we need F to be bigger than 12DMH. But that's good. This is log n. I don't know if you guys can see. Log S, sorry. This is smaller than log S. This is some polylog S. Okay, so just make it bigger than all of them. It's still polylog. And polylog S is good enough because then F to them is poly S. Okay, so this was soundness.
Sorry, why did we need, I think I just noted down, why did we need F to them to be poly S again?
Oh, good. Why do we need, you're saying why can't it be bigger? Because we want our PCP to be of, so the question is, just to recap, why do we insist that F is not bigger? Why does it have to be polynomial related to F? And the reason is, we want the PCP to be of size poly S. We want the PCP A to be not, we want it to be efficient. We want to efficiently convert a witness to a PCP. And the PCP grows with F to the M. Much more. It's like F to the 3M, and it needs to be repeated. And F to the M is poly. So, okay, if this is bigger than poly, if F is more than poly H, then F to the M will be more than poly H to the M. So that's why we want it to be, it's for the sake of efficiency, for the PCP to be small or polynomial related to the circuit.
So just so I understand, so here you're saying that the randomness complexity is polylog n. Now normally you'd be like, okay, the proof size is just 2 to the randomness complexity, but here you've been like more smart, right? Like you've found a way to make the proof shorter than it would be otherwise.
Okay, good. So now let's go to the, well, we didn't do the complexity yet, but yeah, you're a bit ahead of me, but you're totally right. So now, so far we talked about soundness. Completeness is one because the GKR is complete, has completeness 1, so the sum check has completeness 1, so we're good. We talked about sum checks. Any question about soundness? Any question about the soundness? Okay. Let's talk about the complexity. The randomness complexity and the query complexity. So how much query and randomness do we need? So the randomness complexity is, well, there's 2D. So let's put here randomness. So there's 2D sum checks. So the verifier he interacts with his oracle on 2D sum checks. So for each 2D sum checks, he needs to toss coins. Now, how much coins does he toss? Well, he needs to generate R random in F to the 3m. That's each sum check. So it's it's like 3m log F bits of randomness. Now, this is really polylog F. It's like polylog S. It's not log S. Okay, this is really poly, not polylog S, not just log S. So one can be we need to be careful because are we sure we're getting an efficient PCP here? It's a lot of randomness. Are we sure there's no blow up in PCP? And the reason there's no blow up, the reason we have large randomness, yet the PCP is small, is exactly because GKR has this property of forgetting. The fact we actually don't need to open the entire tree. Because of that, we use kind of an additional property. The point is, if you know nothing about the PCP, then, of course, as I said, if it's order log S bits of randomness, it's always the size poly S. But the fact that there are more bits of randomness does not necessarily force our PCP to be bigger. We're just not going to open it like trivially. Like if we did open it trivially, then we would look at all the random, it would be a huge tree, like the depth. But because we do it we pack it efficiently, we're able to get a small PCP even though we have a lot of randomness.
Is it because you're saying each tree is size poly and it's poly trees?
Exactly. Each tree is size poly and they're poly trees. And we're not like, there's a more kind of straightforward way to do it is for each tree append, no, we're kind of doing them in chunks. And so we get the efficiency. Okay, let's go for the query complexity. Okay, I'll just put it here. So let's see. So again, what's the query? He does GKR. So he does 2D sum checks. For each sum check, he needs to read kind of what the answer is. Each answer, so there's 3m rounds that he needs to read. In each answer, he gets kind of a univariate polynomial of small degree. So each answer is not just one field element. It's actually a few field elements. So he gets log F elements times the degree which will be in each sum check, like poly H at most. And this again goes back to the Goldreich, what's exactly the degree of the addi multi, it's polynomial, so it's polynomial in H, it's polylog H. This is kind of the degree of each of the sum check, polynomial. And the degree is affected by the addi and multi, which we assumed the degree is like poly H. But it's still, again, polylog. So this gives, so before we take a break, let me, where are we now? We started actually this class by looking at sum check. So I started this class by telling you, look, sum check is a miracle. Like, given sum check, it gives you everything, everything. And I hope that now you see why. So we start by sum check, and we looked at sum check like, who cares? Okay, the sum, it seems like, why would we need to sum over so many multivariate polynomial? Where does that come up? I don't know, it was like, okay, why am I learning this? But, so now what did we do with it? We started with sum check. We saw, oh, just by doing sum check repeatedly, you can verify any low depth computation. That's pretty amazing. And then we saw that actually you can recover the IP equals P space theorem. That GKR actually gives you the IP equals P space theorem. And now we see GKR actually gives you PCP. And what is GKR? It's just sum checks. Okay, so just these sum checks, you kind of unravel them, and you get a PCP with polylog and queries. And it's like efficient. You can take your input, your witness, and efficiently generate this PCP. And in a very straightforward way, in a sense. You do your computation, you have your witness, you do the computation, you do all the law degree extensions, and you convince round by round. You just lay it out. That's it. And you have a PCP. Okay. Any questions about, yeah, Lali?
So the fact that the GKR tree can be expanded, that relies on just the fact that it consists of these kind of like independent sum checks, or also the fact that sum check itself has that like each query is just a random.
Good. So the question is, again, let's understand, why do we get this PCP that's efficient? Okay, why do we get only poly-sized PCP? And the reason we get is twofold. You said both reasons. Reason number one, that when we do each sum check, after that we can forget about this randomness, and for each VI consider, so we really need to write down only kind of D times F to the M sum checks. Okay, that's D, the depth of the circuit times F to the M sum checks. That's number one. But number two, why is the sum check? Can we write out all the sum check? I mean, the sum check is also an interactive protocol. Can we actually open it up and write the entire thing? And the answer is, well, yeah, but at an exponential cost. But at an exponential cost in M, the number of variables. But here, the number of variables is log. That's important. If M was polylog, we would have been doomed. But it's not just log. We set the parameters so that it's okay. That's what we needed. That's exactly. So why can we open up this entire sum check? It's because we set F to be poly H, and H to the M is S. So we set it up so that opening the sum check requires F to the M kind of answers. F to the M answers. Each one is kind of a low degree polynomial, but that's fine. But F to the M of them, or F to the 3M here, because we have the number of variables is 3M. And we just need to make sure that F to the 3M is polynomial. And to ensure that, we did do some parameter engineering. That's why we didn't go the natural route of taking H to be 2 and M to be log S. That would be natural, but then we would not get. So we actually did need to do some kind of engineering and parameters, like an annoying fiddling of parameters. This setting of parameters that you see over and over in any PCP construction. This is, we're not the first, we're actually the last, if anything, to come to use this. This was used in the 90s in the early PCP constructions. And it's, when you look at it first, like, oh, really? Like, log n over log n? Are you kidding me? Like, couldn't you find something nicer? But this is why, because we want these parameters to be poly. Yeah?
So since you're essentially asking for this to be like a non-adaptive prover, can you just like use the same randomness for each round and like get rid of the D factor in the randomness?
Sorry. So you're saying, your question is, you're saying, are you talking about the fact that this verifier is non-adaptive, or
the prover is non-adaptive here, right?
The prover in the, yes, like it's non-adaptive in the previous sum checks, previous sum checks. Yeah. So then what?
So can you use the same randomness for each round? Like, what would happen if you use the same randomness?
No. Okay. Okay, that's a good question. So you're saying, look, we're doing the sum check d times. Can't we use the same randomness? And the answer is we cannot. Why? Because you should think, if we use the same randomness for different rounds, then you should think of, I'm a prover. I'm like, oh, you're going to use the same randomness for all your rounds. I know that because you're telling me already that you're going to use the same randomness. So now in the first round, I'm going to behave honestly. Just learn your randomness. I'm not going to behave. I'm going to cheat in the first round. Okay, so of course I'm going to cheat. I'm telling you the output is 1 even though it's 0. I'm going to manage to convince you in the first sum check I do. Yeah, because I'm just going to lie consistently with myself. Arrive to to the next layer, no, wrong, still inconsistent. But now I know the randomness, because you're going to reuse. You see, here, the point is the following. The verifier here should behave like an honest verifier in the GKR. If the verifier here, when you use this verifier, he essentially behaves like a GKR verifier. So now you're saying, look, why doesn't he use the same randomness for the different sub-protocols? Because if he did in GKR, then he would fail. Then a cheating prover can take advantage of him.
But isn't there the difference here that this prover is non-adaptive? Like, it doesn't remember the randomness. All it depends on is the tilde I minus 1.
Right.
And so you can't just be like, oh, this is the randomness.
Oh, I see. You're saying, I see. Okay. Now I understand your question. You're saying this guy, this prover is stuck. Okay. Sorry. Now I understand what you're saying. You're saying, look, you're tying the hand of this prover. The prover in GKR, he has power. He sees your randomness, and based on that, he can continue. The honest prover, of course, won't do that, but the cheating prover may. Here, you're saying, I'm not going to let the prover do that to me. I'm going to force him to forget. Because I forced him to forget, can I think of using the same randomness? That's a good question, actually. A very good question. It took me time to understand what you're asking.
Can you use the same?
It's great point.
Malicious verifier you just said to break that?
Well, no, because So your point is the following: that you know what? Use the same randomness in all the sub-protocols. Now, in the GKR, it's a big problem because the prover, he knows what you saw, and he'll use that like he knows the randomness. But in the PCP GKR prover, his hands are tied.
Yeah, but the fact that if the prover knows that you're going to do this, then he might be able to engineer all of his responses in a way that takes advantage of the correlation of the randomness.
Right, by exactly using the same verifier you said, you pretend you have that verifier that cheats, but then you use the same randomness. Now this tree follows that verifier strategy. Then shouldn't that break it?
I think even if it is sound, it doesn't follow just from GKR soundness.
Yeah, it could be sound, but there's this correlation between the randomnesses, which the prover would know about in advance, right? So even though he can't remember the randomness, he can engineer a strategy to take advantage of the fact that the randomness will be used.
Okay, let me say the following to close this discussion. The discussion is super interesting. The question you raised is super interesting. You know, we have one PSET in this class. You gave me a great idea for a question. By the way, before we break, I just want to make a quick announcement. So I wrote in the website that the PSET will come later during this class because I thought it would be good to cover more material. But I know that I wrote it pretty close, to the break, and maybe that's so maybe I'll put it out earlier, give you 2 weeks, and just because I don't want you to sit with it too long, it's just annoying. But if you feel like the time doesn't work and you want an extension, just let me know. I don't really care. Tell me the truth. I just want you to think about it and have fun with with the material. Yeah.
When we argue soundness, are we using any sort of union bound-like thing?
Yeah, exactly. We're doing a union bound. Yeah, yes, exactly. Because in the soundness, we say the following. We say that so essentially we're talking with a prover and a GKR prover. And we're saying for the GKR, even like a tied GKR prover, as you mentioned, even it's a GKR prover with tied hands. So for this prover to cheat, so the output is false. That's kind of, he cheated. So somewhere he needs to cheat in one of the GKRs. One of the sum checks, he needs to go from false to true, somewhere. Because at the end, you're verifying the, he put here a witness. So he put in this guy a witness. That witness is false because there's no satisfying assignment. So he put something that's actually false. Oh, 1 second, there is something. Okay, sorry, now I remember. There is something, there is a low degree test to do. We'll get back to that. Sorry. We'll get back to the low degree test. But so you're talking with you're talking with a GKR prover. And this prover, the only way he can convince you is to go from like a false statement to a true statement. Because at the end, and to do that, you need to break one of the sum checks. So to break one of the sum checks, you have 2D sum checks. And now I'm using a union bound to say that the probability that you kind of manage to break one of them is 2 to the d times the probability that you manage to break one of them.
Okay, so yeah, but then back to discussion where like you're sharing randomness. So does union bound help here?
You're saying, oh, because of the.
Because it didn't assume independence of them.
Okay, so is this related to this question? Okay. Actually, I don't think so because union bound in general, it can be correlated. A union bound in general says that the probability that this or this, I don't care how they're correlated. It's small or equal to the probability of this plus the probability of this. So the correlation here, the union bound is very easily used in any situation. Just at the probability that you have an event, you cheated on test 1, you cheated on test 2, you cheated on test 3. I don't care how they're correlated. The probability that you cheat on one of them is small or equal than. Yeah? But actually, before we break, sorry, there is a low degree extension. What?
In the first time around.
Exactly.
Because in GKR, you can just use brute force.
Good. Okay. Sorry. Good. I love you guys. Yeah, V, okay, check V0 tilde is low degree. Because in GKR, the verifier has the input, which is the witness. He computes the low degree extension by himself. Here, the prover is giving it to him. What if he didn't give a low degree? So we do need one low degree test in the input. Other than that, it's GKR, black box. But we do need this. And by the way, note that we're using the GKR. The GKR has actually properties. And now I want to go back to the succinctness, because actually you're saying, can't you do it with any succinct protocol? And the answer is maybe, but there's also this point which is problematic. That in GKR, it's nice because you just check one point in the low degree extension. And we can verify that you do the low degree extension. There's a low degree test that I didn't talk to you about, but we'll mention that after the break. So there's a GKR, you can verify the verifier. To verify, all he needs to do is take his input and compute only 1 point or 2 points in the low degree extension of that input. This is actually used here. Because now the verifier doesn't have the input, the witness, the prover has it. He's going to put it in the sky. And now you can't read the entire input, that's the witness. But you can read, like, what the kind of succinct protocol tells you to read, And so this part is important in the GKR. Okay. Questions before we break? Okay, so after we'll take a 5 minutes break, and then we'll talk quickly about the low degree test, wrap up the information theory, and go to cryptography. Okay.